Hey guys, tonight we are defeating gravity. The castle walls are built to last forever, but we have built a machine that turns physics into a weapon. We are joining the medieval siege engineer. We are going to construct the wooden giant that ended the age of stone fortresses. This is a story about leverage, tension, and the heavy thud of the counterweight. So, before you get comfortable, take a moment to like the video and subscribe. Now, hear the timber creak, and let's ease into tonight's journey together. The siege camp sprawls across the valley floor like a temporary city born of mud and desperation. It is the autumn of 1247, and the rains have come early this year. The ground beneath 10,000 feet has been churned into a thick, sucking morass that clings to boots and wagon wheels with equal tenacity. Every step is a negotiation with the earth itself. The mud is not the clean brown of tilled fields, but a grey-black slurry mixed with ash from cooking fires, the waste of horses and men, and the detritus of an army that has been camped here for 3 months. It squelches and belches tiny pockets of trapped air when you walk through it. At night, when the temperature drops, the surface hardens into a crust that breaks beneath your weight, sending cold, viscous mud over the tops of your boots. The castle sits on its hill like a crown of pale stone. Its walls are limestone, quarried from the bedrock beneath it, and in the weak afternoon light, they seem to glow with an inner luminescence. Those walls are 12 feet thick at the base, tapering to 8 feet at the crenellations. They rise 40 feet from the dry moat that encircles the fortress. The towers at each corner climb another 20 feet beyond that, crowned with conical roofs of dark slate. From the siege camp, you can see the banners snapping in the wind atop those towers, bright squares of red and gold that announce the defiance of the garrison within. The castle has its own well, its own granaries, its own smithies. It was built to endure. It was built to laugh at armies camped in the mud below. But the siege engineer knows something the castle's builders did not anticipate. He knows that height can be overcome, that thickness can be breached. That stone, for all its seeming permanence, is brittle. Stone does not bend, it shatters. His tent stands near the center of the encampment, distinguished from the thousands of other tents by its size, and by the nature of the traffic that flows in and out. It is not a pavilion of silk and embroidered banners like those of the lords and knights. It is a working tent, a structure of heavy canvas dyed the color of old blood by some tanning process that also makes it resistant to water. The tent is 30 feet long and 20 feet wide, with a ridge pole 10 feet off the ground. The canvas is stretched tight over a framework of ash poles, lashed together with hemp rope that has been soaked in pine tar to prevent rot. The whole structure smells of tar and canvas and the peculiar, resinous scent of the treated wood. Inside, the tent is a workshop and a scriptorium combined. Trestle tables line the walls, their surfaces covered with drawings, calculations, and models. There are sketches on parchment, diagrams scratched into wax tablets, and full-scale templates drawn on sheets of stretched linen. In one corner stands a small forge, its chimney venting through a carefully cut hole in the tent's roof, patched around with scraps of leather to keep the rain out. The forge is cold now, its coals gray and dead, but the smell of hot iron and coal smoke has permeated the fabric of the tent itself. There are tools everywhere, adzes and augers, draw knives and planes, chisels of every size, mallets with heads of lignum vitae, measuring rods marked in feet and inches, and the engineer's own private system of units that he has developed over decades of building. The engineer himself is a man of perhaps 50 years, though the rigors of his profession have aged him beyond his time. His hair is iron gray, cut short in a style that is practical rather than fashionable. His hands are massive, the fingers thick and scarred from a lifetime of working with tools and timber. There is a burn across the back of his left hand, shiny pink tissue in the shape of a horseshoe, from the time a hot poker slipped in his grip. His eyes are dark brown, set deep beneath heavy brows, and they have the focused quality of a man who sees the world in terms of forces and resistances loads and stresses, the invisible architecture of physics. He stands now at the largest of the tables, looking down at a drawing. The drawing is rendered in charcoal on a sheet of linen 4 feet wide and 6 feet long. It shows, in precise detail, the machine that will break the castle. The locals call it a trebuchet, from an old French word meaning to overturn. The engineer thinks of it simply as the machine, his machine, the fifth such device he has built in his career and the largest. The drawing shows the fundamental simplicity of the design. A massive arm, perhaps 40 feet long, pivoting on an axle mounted between two triangular frames. The short end of the arm, perhaps 12 feet long, carries a box filled with weight. The long end, 28 feet from the pivot to its tip, carries a sling. When the counterweight is released, it falls, and the long arm whips upward with terrible speed. The sling releases its projectile at the apex of the arc, sending a stone ball weighing 300 pounds through the air in a parabola that will terminate somewhere among the buildings of the castle. Or, if the engineer has calculated correctly, against the base of the south wall, where the foundations meet the bedrock, and where repeated impacts will shatter the mortar and crack the stones until the wall collapses inward. The principles are ancient, known to the Greeks and Romans, refined by the engineers of Byzantium and the Arab caliphates, but the scale is new. Trebuchets have grown larger with each generation of builders as engineers have learned to manage the tremendous stresses involved. This machine, when complete, will stand nearly 60 feet high at the tip of its raised arm. The counterweight will exceed 10 tons. The forces involved when that weight falls will be enough to tear the machine apart if even a single component is weak or misaligned. And so the engineer has spent 3 weeks planning, calculating, drawing and redrawing. He has consulted with the carpenters and the blacksmiths. He has walked the ground where the machine will stand, pacing off distances, checking sight lines to the castle wall, considering the angle of the slope. He has tested samples of the timber, checking for flaws, for rot, for the subtle twisting of the grain that might indicate weakness. He has rejected whole trees based on nothing more than a feeling, an instinct developed over decades. Now, finally, the planning is complete. The timber is selected and cut. The iron fittings are forged. The rope is ready. The grease is prepared. The carpenters and laborers are assembled. Tomorrow they will begin. But first, there is the ground to consider. The machine cannot be built on mud. The forces it will generate when it fires are immense, concentrated into the small footprints of its two frames. If the ground is soft, those forces will drive the frames down into the earth. The machine will tilt. The arm will strike the ground instead of swinging freely, and the whole apparatus will either fail to fire or tear itself to pieces in the attempt. The ground must be solid. It must be level. It must be prepared. The engineer steps out of his tent as dawn breaks over the siege camp. The sky is the color of old pewter, heavy with clouds that promise more rain. The air is cold enough that his breath steams. Around him, the camp is waking. Cooking fires are being kindled, sending tendrils of smoke into the still air. Men emerge from tents, stretching, coughing, relieving themselves in the designated latrine trenches that have been dug downslope from the camp. The smell of wood smoke mingles with the smell of cooking porridge, horse dung, wet canvas, and 10,000 unwashed bodies. The engineer ignores all of this. His focus is on the ground. The site he has chosen is 200 yards from the castle wall, well within range, but far enough that the defenders' crossbows and archers cannot easily harass the workers. It is upslope from the main camp, on a slight rise that provides good drainage. The ground here is better than the quagmire below, but it is still not ideal. The topsoil is 8 inches of that grey mud, beneath which is a layer of clay, and beneath that, finally, bedrock. The engineer needs to reach that bedrock. Or, failing that, he needs to create an artificial foundation strong enough to support 10 tons of falling weight. A crew of 30 laborers has been assigned to him. They assemble now in the pre-dawn gloom, carrying shovels and mattocks, wooden buckets and wicker baskets. They are men from the baggage train, too old or too young or too injured to fight in the line, but still capable of hard labor. They wear shapeless tunics of undyed wool, leather jerkins, and boots that are more patches than original material. Their faces are expressionless, patient with the patience of men who have done hard labor all their lives and expect nothing else. The engineer addresses them briefly. His voice is hoarse from years of shouting over the noise of construction sites. He speaks in the vernacular, the common tongue of the region, rather than the French of the nobility or the Latin of the clergy. He tells them what needs to be done. The mud must be removed. The clay must be excavated down to bedrock. The hole must be 40 feet long and 20 feet wide, oriented perpendicular to the castle wall. It must be level, checked with string lines and spirit levels. It must be exact. The men nod and set to work. The labor is brutal. The mud comes up easily enough, thrown into baskets and carried away to be dumped downslope. But the clay beneath is dense and sticky, resistant to shovels. The laborers use mattocks to break it up, swinging the heavy tools in a rhythm that is as old as agriculture itself. The mattock rises, pauses at the top of its arc, then falls with the laborer's full weight behind it. The blade, iron sharpened to a chisel edge, bites into the clay with a sound like ripping fabric. The laborer levers the handle, pries up a chunk of clay the size of a man's head, then steps back as another man scoops it into a basket. Over and over, hour after hour. The engineer watches, pacing the perimeter of the excavation, checking the depth with a measured pole. Every few feet, he stops and stretches a string line across the hole, checking it with a small spirit level he carries in a leather pouch at his belt. The level is a precious tool, a glass vial half filled with alcohol, sealed with wax, set into a wooden block. When the block is placed on a surface, the bubble in the vial will migrate to the highest point. If the bubble is centered between two scribed marks, the surface is level. It is simple, elegant, and indispensable. By midday, the excavation is 4 feet deep, and they have reached bedrock. The bedrock is limestone, the same pale stone from which the castle is built. It is not perfectly level, but it is close enough. The engineer calls a halt to the digging. The men lean on their tools, breathing hard, their tunics soaked with sweat despite the cold. They will have a short rest and a meal of bread and beer, and then the real work will begin. The foundation of the machine consists of 3 massive beams called sleepers. These are oak trees that have been felled, stripped of bark, and hewn square. Each beam is 30 feet long, 2 feet wide, and 2 feet deep. They weigh, the engineer estimates, approximately 3 tons each. Getting them to the site will require teams of oxen and a wheeled cradle designed specifically for the purpose. The first sleeper beam arrives in the early afternoon, dragged on a low cart pulled by 8 oxen. The cart's wheels are 5 feet in diameter, bound with iron, and they leave deep ruts in the mud of the access path. The oxen strain in their harness, heads low, hooves churning the ground. The teamster walks alongside, calling encouragement, occasionally touching a flank with his goad. Behind him, carpenters walk with ropes and poles, ready to guide the beam into position. The cart is maneuvered to the edge of the excavation. The sleeper beam rests on wooden rollers, greased with tallow. Ropes are attached to iron rings at either end of the beam. Men take up the ropes, 15 to each side. The engineer positions himself at one corner, watching the angles, calling instructions. The teamster unhitches the oxen and leads them clear. On the engineer's signal, the men pull. The beam shifts on its rollers, sliding forward with a low, groaning sound. It moves perhaps 6 inches. The men reset their grips and pull again. Another 6 inches. The process is agonizingly slow. The beam must be kept parallel to the long axis of the excavation. If it tilts, if it slides sideways, it could roll, and 3 tons of rolling oak will crush anything in its path. It takes an hour to move the beam 30 feet from the cot to the edge of the excavation. Now comes the delicate part. The beam must be lowered 4 feet into the hole, settling onto the bedrock without tipping. Carpenters have prepared a system of ramps and levers for this purpose. Thick planks are positioned to guide the beam's descent. Wooden wedges stand ready to check its movement if it slides too fast. The engineer takes personal control now, his voice sharp and commanding. The ropes are repositioned, running through iron pulleys anchored to stakes driven deep into the ground beyond the excavation. The men on the ropes are not pulling now, but paying out slowly, controlling the descent. Other men work the levers, massive oak poles thrust under the beam, using fulcrums to guide it. The beam tips. For a moment, it balances on the edge of the excavation, 3 tons of oak poised over the void. Then it begins to slide, slowly at first, then faster. The men on the ropes lean back, their feet skidding in the mud, fighting to slow it. The beam accelerates down the ramp with a deep bass rumble. It strikes the bedrock with a boom that echoes across the siege camp, a sound like thunder, like the earth splitting. Dust and chips of limestone spray from the impact point. The beam bounces slightly, settles, and is still. The engineer is already in the excavation, running his hands over the beam, checking for cracks. Oak is strong but brittle when struck. A crack in a sleeper beam would compromise the entire structure, but the wood is sound. The impact has merely compressed the surface slightly, driven some of the fibers into each other, but the beam is whole. He checks the position with string lines. The beam is 3 inches out of alignment, not acceptable. Men climb into the excavation with iron pry bars. They lever the beam, shifting it millimeters at a time, while the engineer watches his strings. When the beam is aligned, he checks it for level. The bubble in his spirit level sits fractionally to one side. The beam must be shimmed. Thin wedges of oak, plain to precise tapers, are driven under the low end of the beam. Each wedge shifts the beam upward perhaps a 16th of an inch. The engineer checks, rechecks, has another wedge driven, checks again. It takes 40 minutes to level the beam to his satisfaction. When it is done, the bubble sits precisely between its marks, and the beam will not rock when pushed. The second sleeper arrives, and the process repeats. This beam runs perpendicular to the first, positioned at the front of the excavation, toward the castle. It must be exactly parallel to the first beam, exactly 20 feet away. The engineer stretches string lines between measured points, creates a geometric framework in the air above the excavation. The carpenters work within this invisible cage, positioning the second beam with painful precision. The third sleeper goes at the rear of the excavation, parallel to the second, creating a rectangle 20 feet by 30 feet. When all 3 beams are in place, leveled, and aligned, the engineer has the carpenters drill holes through them at regular intervals. The holes are 2 inches in diameter, drilled with a T-auger that requires 2 men to turn. The drilling is slow. Oak resists the bit, and the men must stop frequently to clear the shavings from the hole and to sharpen the auger's blade. Into these holes go wooden pins, oak dowels 2 inches thick and 2 feet long. The pins are driven through the sleeper beams and into the bedrock beneath, anchoring the entire foundation. Each pin is driven with a sledgehammer, struck with blows that ring across the siege camp. The engineer watches each pin, listening to the sound it makes. A solid pin driven into sound rock produces a clear, high note. A pin striking a void or a crack sounds dull, muffled. When he hears that muffled sound, the pin is withdrawn. The hole is filled with a mixture of limestone chips and lime mortar, and a new hole is drilled. By sunset of the second day, the foundation is complete. 3 massive oak beams, locked together and pinned to the bedrock, form a platform that will not shift, will not settle, will not betray the machine that will be built upon it. The engineer allows himself a moment of satisfaction. The foundation is invisible, will be buried beneath other timbers, will never be seen or appreciated by anyone but himself. But he knows that everything depends on it. A house built on sand will fall. A siege engine built on mud will destroy itself, but this machine has a foundation that will endure. The next phase is the construction of the A-frames. These are the two triangular structures that will support the axle, and through the axle, the entire weight of the swinging arm. Each A-frame consists of two uprights and a cross brace. The uprights are pine trees, selected for straightness, each 30 feet long and 18 inches in diameter at the base, tapering to 12 inches at the top. They have been hewn to an octagonal cross-section, a compromise between the strength of a round log and the convenience of a squared beam. The wood is green, cut less than a month ago, and still heavy with sap. Green wood is stronger in some ways than seasoned timber. It is more flexible, less likely to split when stressed. But it is also heavier, harder to work, and it will shrink as it dries, which must be accounted for in the joinery. Each upright weighs nearly a ton. They lie now on the ground beside the foundation, like felled giants. Their bark has been stripped away, revealing the pale yellow wood beneath. The surface is smooth where the adze has pared it, rough where the saw has cut across the grain. The engineer walks the length of each timber, examining it for flaws. He finds a knot in one, a dark, hard swirl where a branch once grew. He marks it with a piece of charcoal, notes its position, calculates whether it will affect the timber's strength. The knot is 18 feet from the base, which will place it above the point of maximum stress. Acceptable. The uprights must be joined at the top to form the apex of the A-frame. The joint is a simple lap joint, the two timbers crossed and notched so that they nest into each other. The notching is done with axe and adze, the carpenters working with a precision that seems at odds with the brutality of their tools. A carpenter marks the outline of the notch with a scribe, a sharp iron point that scratches a line into the wood. He follows this line with an axe, cutting a series of vertical chops across the grain. Each blow of the axe sends chips flying. When the notch is roughed out, he switches to an adze, refining the surface, removing the high spots, creating a flat bed for the other timber to rest upon. The two uprights are laid side by side on the ground, their tops overlapping. The carpenters check the fit of the joint. It is too tight. More wood must be removed. They work in increments, shaving away perhaps a quarter inch with each pass, checking the fit, shaving more. When the joint is correct, the two timbers will slide together with firm resistance, compressing the wood slightly, creating a joint that will be strengthened by the weight it bears. But the joint cannot rely on friction alone. It must be pinned. The carpenters drill a hole through both timbers where they cross, using a 2-inch auger. The hole must be precisely perpendicular to the joint, precisely aligned. A misaligned hole will weaken the timber. The drilling takes an hour, the carpenters pausing frequently to rest and to clear the shavings. When the hole is complete, they drive an oak pin through it, a pin that has been shaped on a lathe, turned to a perfect cylinder 2 inches in diameter and 4 feet long. The pin is driven with a sledge, and as it goes in, it compresses the fibers of both timbers, locking them together. The cross brace is a horizontal timber that will connect the two uprights at a point 10 feet above the ground. This timber is oak, 1 foot square and 12 feet long. It is mortised into the uprights. The mortise is cut with chisel and mallet. A mortise is a rectangular hole, in this case 4 inches wide and 8 inches deep, cut into the side of each upright. The cross brace has tenons cut on each end, projections of wood 4 inches wide and 8 inches long that will fit into the mortises. Cutting a mortise is painstaking work. The carpenter begins by drilling a series of holes within the outline of the mortise using a 1-inch auger. These holes remove most of the waste wood. Then he takes a chisel, a heavy tool with a blade 4 inches wide, and begins paring away the remaining wood. The chisel is struck with a mallet, a hardwood hammer that will not damage the chisel's handle. Each blow removes a thin shaving. The carpenter works to a line, checking the depth of the mortise with a measuring stick, checking the squareness with a tri-square. When both mortises are complete, the tenons on the cross brace are fitted. The tenons are slightly oversized, deliberately. They must be trimmed to fit. The carpenter offers the tenon to the mortise, sees where it binds, marks those spots with charcoal, and planes them down. Offer mark plane. Offer mark plane. The cycle repeats until the tenon slides into the mortise with firm resistance. Then it is withdrawn. The end of the tenon is coated with hide glue, a hot liquid made by boiling animal skins and bones, and the joint is assembled. The glue will dry rock hard, adding strength to the mechanical join. Now the first A-frame must be raised. Two 30-foot timbers, joined at the top, connected by a cross brace 10 feet from the ground, the whole assembly weighing perhaps 3 tons. It lies on the ground like a fallen gate, and it must be lifted to vertical and positioned on the sleeper beams. This is work for a gin pole. A gin pole is one of the engineer's most useful tools, a simple crane consisting of a single vertical pole with a pulley at its top. The pole itself is a pine tree 40 feet long and 2 feet in diameter at the base, set into the ground with a foundation of rocks and tamped earth. The pulley is iron, a grooved wheel 6 inches in diameter, mounted on an iron axle at the top of the pole. A rope runs through the pulley, with one end attached to the load, and the other end pulled by men or animals. The gin pole stands now just beyond the foundation, tall and stark against the grey sky. The engineer positions it carefully, checking sight lines, ensuring that when the A-frame is raised, it will swing into position over the sleeper beams. Ropes are attached to the apex of the A-frame. The ropes run up to the gin pole's pulley and back down to the ground, where they are wound around a capstan, a horizontal drum turned by men pushing on radial spokes. The capstan is the heart of the operation. As the men turn it, the rope winds around the drum, shortening the free length, drawing the A-frame upward. But simply lifting the A-frame would cause it to slide across the ground. It must pivot. The base of each upright is positioned on the sleeper beams at the points where it will ultimately stand. Wooden chocks hold it in place. As the apex is lifted, the frame will rotate around these pivot points, the uprights sliding across the sleeper beams until the frame is vertical. The engineer gives the signal. 16 men put their shoulders to the capstan's spokes and push. The capstan begins to turn with a slow, grinding sound. The rope tightens, lifting slightly off the ground. The men push harder. The rope goes taut, thrumming with tension. Still, the A-frame does not move. The engineer calls for grease. The bases of the uprights are coated with tallow, making the wood slippery. The men push again. This time, the A-frame shudders and begins to move. The apex lifts off the ground, rising perhaps 6 inches. The uprights slide across the sleeper beams with a low, groaning sound. The wood complains, fibers compressing, sap squeezing out from the pressure. The capstan turns. The men push in a rhythm now, a low chant keeping time. The A-frame rises slowly, the angle increasing degree by degree. When it reaches 30 degrees, the weight shifts and suddenly the frame is lighter. The men at the capstan can feel it, the reduced resistance. They push faster, and the frame rises more quickly. But speed is dangerous. If the frame rises too fast, it will overshoot vertical and fall forward, crashing into the foundation and destroying itself. The engineer shouts a warning. The men at the capstan slow their pace. Carpenters with ropes attached to the cross brace stand ready to steady the frame, to check its motion if it swings too far. At 60 degrees, the frame is very light, almost buoyant. The weight is nearly balanced over the pivot point. The men at the capstan push gently now, feeling their way, watching the angle. 70 degrees, 80 degrees. The frame trembles in the wind, 30 feet of timber balanced on 2 narrow points. 85 degrees. The engineer raises his hand, and the capstan stops. Carpenters with wooden props rush in, setting braces against the uprights to hold the frame at this angle. The props are poles of ash, 10 feet long, one end dug into the ground, the other pressed against the timber. They are not strong enough to support the frame indefinitely, but they will hold it while the final adjustments are made. The engineer checks the position. The bases of the uprights must be exactly 20 feet apart, centered on the sleeper beams. He measures with a knotted rope, a rope that has knots tied at precise intervals. The distance is correct. He checks for vertical with a plumb barb, a lead weight on a string. When the frame is vertical, the string will hang parallel to the upright. It does not. The frame leans slightly forward toward the castle. The men at the capstan take up the slack, lifting the apex another few inches. The engineer checks again, still not vertical but closer. Another adjustment, another check. It takes an hour to position the frame exactly. When it is done, the uprights are vertical within a quarter-inch over 30 feet. The bases are spiked to the sleeper beams with iron nails 6 inches long, driven through pre-drilled holes. The nails are not structural, they cannot bear the weight, but they will prevent the frame from sliding. Then the frame is braced. Diagonal timbers run from the cross brace to stakes driven into the ground 20 feet away, creating a tripod structure. These braces are temporary, but they will hold the frame secure while the second A-frame is raised and the two frames are connected. The second A-frame goes up the following day. The process is identical, but the crew has learned from the first raising. They work more smoothly, more confidently. There are fewer false starts, fewer corrections. The second frame is vertical and braced by mid-afternoon. Now the two frames stand like skeletal sentries, 40 feet tall, 20 feet apart, dominating the skyline of the siege camp. Between them, the space is empty, waiting for the axle. The axle is the heart of the machine. It is the point around which everything turns, the axis upon which the entire engine pivots. It must be strong enough to support the weight of the arm, the sling, and the projectile. It must be smooth enough to rotate freely despite the massive forces acting upon it, and it must be precisely positioned. For this machine, the engineer has chosen an iron axle. Iron is expensive, difficult to work, but infinitely stronger than wood. The axle is a bar of wrought iron 6 inches in diameter and 14 feet long. It was forged in sections by a team of blacksmiths working day and night for a week. Each section was heated to white heat in a charcoal furnace, hammered to shape on an anvil, then welded to the next section by heating the ends until they were nearly molten and hammering them together, forcing the metal to flow and merge. The finished axle weighs nearly half a ton. It is not perfectly round. Wrought iron cannot be forged with such precision, but it has been filed and rasped to remove the worst irregularities, and it will be wrapped in greased leather where it contacts the bearings. The bearings are the uprights themselves. At the apex of each A-frame, where the two timbers cross, a hole has been cut. The hole is 6.5 inches in diameter, slightly larger than the axle. It has been lined with bronze bushings, thick rings of cast bronze that will bear the friction of the rotating axle. Bronze is softer than iron, and it will wear rather than the axle wearing. When the bushings wear out, they can be replaced. Getting the axle into position is a delicate operation. It must be lifted 14 feet into the air and threaded through the holes in both A-frames simultaneously. If it tilts, if it binds, it could fall, and half a ton of iron falling from 14 feet will kill anyone beneath it. The engineer uses the gin pole again, repositioning it between the two A-frames. The axle is suspended from the gin pole by a sling of rope looped around its center point. As the capstan turns, the axle rises, slowly, swaying slightly. When it is level with the holes in the A-frames, the engineer calls a halt. Carpenters with long poles position themselves at either end of the axle. They will guide it into the holes, pushing and pulling as needed. The engineer stands on a platform lashed to one of the A-frames, level with the bearing, watching the alignment. The axle is moved horizontally, sliding through the air like a giant needle threading through two eyes. The end approaches the first hole, too high. The capstan pays out rope, lowering the axle a few inches. The engineer signals forward. The axle slides into the hole, the iron scraping against the bronze bushing with a low, ringing sound. The second end is more difficult. The axle must be perfectly aligned with both holes, and the holes are 20 feet apart. A quarter inch of misalignment at this distance becomes a visible gap at the far end. The carpenters work their poles, shifting the axle minutely. The engineer watches from his platform, calling adjustments. Up a hair, left, forward, back. The axle slides into the second hole. It binds. The engineer examines the fit. The axle is tilted slightly. The far end is withdrawn. The angle is corrected, and it is tried again. On the third attempt, the axle slides home. It projects 6 inches beyond the bearing on either side, enough to be wedged in place with wooden keys, tapered blocks of oak driven into notches cut in the ends of the axle. The keys will prevent the axle from sliding sideways. The engineer checks the rotation. He grips the axle and tries to turn it. It resists the friction of bronze on iron. He signals for the grease. Animal fat, rendered from sheep and cattle, mixed with beeswax and pine resin, heated until liquid, cooled until it is the consistency of soft butter. This is the grease that will lubricate the bearings. It is packed into the gap between the axle and the bushings, forced in with wooden paddles, worked into every crevice. When the bearings are fully greased, the axle turns smoothly, requiring only a modest force to overcome the inertia. The engineer tests it again and again, turning the axle a few degrees, feeling for rough spots for binding. He finds a spot where the rotation is slightly rougher. More grease is applied. The rough spot smooths out. He is satisfied. With the axle in place, the structure of the machine is beginning to emerge. The two A-frames, connected by the axle, form a rigid portal, but they must be braced to resist lateral forces. When the arm swings, it will try to twist the frames, to push them sideways. Without bracing, the frames would flex and eventually fail. The bracing consists of diagonal timbers running from the base of one upright to the cross brace of the opposite upright, creating an X pattern on each side of the machine. These timbers are pine, 1 foot square in cross-section, mortised into the uprights and cross braces. The mortises are cut with the same painstaking care as before, and the timbers are fitted with hide glue and wooden pins. When the bracing is complete, the engineer tests the rigidity of the structure. He has men push against the uprights, trying to rock the frames. The structure barely moves. He is satisfied. The frame is solid, capable of withstanding the enormous forces that will be unleashed when the machine fires. Now comes the arm. The arm is the most critical component of the machine, the element that translates the fall of the counterweight into the flight of the projectile. It is a single beam of oak, 40 feet long, tapering from 2 feet square at the axle to 1 foot square at the tip. The taper is essential to save weight at the long end of the arm while maintaining strength at the pivot point where the stresses are greatest. The oak for the arm was selected with extraordinary care. The engineer himself went into the forest with the woodcutters, examining trees, rejecting dozens before finding one that met his requirements. It had to be straight, free of twists, free of large knots. The grain had to run straight and true from one end to the other. The tree had to be large enough to yield a 40-foot beam 2 feet square at the base. They found such a tree, a white oak growing on a hillside where the soil was deep and the competition for light was fierce. The tree had grown tall and straight, reaching for the sun. It was felled with axes, the chips flying as the woodcutters worked in shifts, chopping from both sides until the tree groaned and began to lean and finally fell with a crash that echoed through the forest. The tree was limbed and bucked, the top and branches removed, leaving a clean bole 45 feet long. It was hauled to the siege camp by a team of 20 oxen, dragged on a sledge of logs. the journey taking 2 days. At the camp, it was placed on sawhorses and hewn to shape. Hewing is the process of removing the sapwood and shaping the log into a beam. It is done with a broadaxe, a tool with a blade 12 inches wide and a handle 3 feet long. The broadaxe is swung in a horizontal arc, slicing into the side of the log, removing a chip of wood with each stroke. The work is rhythmic, hypnotic, the axe rising and falling, the chips flying. A skilled hewer can remove wood in slices as thin as paper, leaving a surface almost as smooth as if it had been planed. The arm was hewn over the course of a week, the shape emerging gradually from the rough log. The taper was achieved by measuring and marking at intervals, creating a template that the hewers followed. When the rough shaping was done, the beam was planed to smooth the surface and remove the axe marks. The planing was done with a long plane, a tool 4 feet long with a blade set in its base. 2 men worked the plane, one pulling, one pushing, the blade shaving off thin curls of wood that piled up like golden snow. The completed arm is a thing of beauty, 40 feet of pale oak, the grain running straight and true, the surface smooth to the touch. It weighs, the engineer estimates, approximately 2 tons. At the thick end, where it will mount on the axle, a square hole has been cut through the beam. This hole is 6.5 inches square, sized to fit over the iron axle. The hole is lined with iron plates bolted to the wood, plates that will bear against the axle and prevent the wood from crushing under the load. Mounting the arm on the axle is another delicate operation. The arm must be lifted, tilted, and slid onto the axle, the square hole aligning with the round axle. But the hole is square and the axle is round. How can a square hole fit on a round axle? The answer is that it doesn't fit tightly. The square hole is larger than the circle inscribed within it. The arm will rest on the axle at 4 points, where the corners of the square hole contact the round surface of the axle. This is intentional. It allows the arm to be mounted and dismounted relatively easily, and it provides a predictable bearing surface. But there is a problem. If the arm simply rests on the axle, it will slide sideways, falling off when the machine fires. It must be locked in place. The engineer's solution is a wooden collar, a block of oak 1 foot square and 2 feet long, with a round hole 6 inches in diameter cut through its center. This collar will be slipped onto the axle, positioned against the arm, and wedged in place. The wedging will prevent the arm from sliding. The arm is brought to the machine on a wheeled cart, lying on its side. Ropes are attached to both ends. The gin pole is repositioned yet again, this time beside the machine. The plan is to lift the arm vertically, raise it above the axle, then lower it onto the axle from above. The lifting begins. The ropes tighten, the cart's suspension compresses, and slowly the arm lifts off the cart. It rises, spinning slightly in the air, 2 tons of oak suspended by nothing but rope and human muscle. The men at the capstan push, the drum turns, the rope winds. The arm rises foot by foot. When it is 15 feet off the ground, it is maneuvered horizontally, swung on the rope like a pendulum until it is positioned over the axle. The engineer watches from his platform, judging the alignment. The arm is too far forward. The capstan pays out rope, lowering the arm slightly. Men with poles push the arm backward. It swings ponderously. Too far. They pull it forward. Small adjustments, endlessly repeated, until the square hole in the arm is aligned with the axle below. Then the descent. The rope pays out slowly, the arm lowering millimeter by millimeter. The engineer guides it with his hands, feeling for the axle. The hole approaches the axle. Contact. The iron plates inside the hole scrape against the iron axle. The arm settles, rocking slightly, then is still. The engineer checks the balance. The arm is 40 feet long, but it is not symmetrical. 28 feet extend on one side of the axle, the long end, where the sling will attach. 12 feet extend on the other side, the short end, where the counterweight will hang. The weight of the wood is not evenly distributed because of the taper. The long end is lighter. Without any additional weight, the arm balances with the long end up and the short end down. This is correct. When the counterweight is added, it will overwhelm the weight of the arm, pulling the short end down. The machine will rest with the long arm pointing at the sky, ready to fire. But before the counterweight can be added, the short end of the arm must be fitted with the pivot points for the counterweight box. These are iron hooks, massive U-shaped forgings, each weighing 50 pounds. They are bolted through the arm at the very end, two hooks side by side, positioned so that the counterweight box will hang between them. The holes for the bolts are drilled with a 2-inch auger, drilled from both sides to meet in the middle. Even with 2 men turning the auger, it takes hours to drill through 2 feet of oak. The bolts themselves are iron rods 2 inches in diameter and 3 feet long, threaded at both ends. They are driven through the holes, and massive iron nuts are threaded onto the ends and tightened with a wrench 4 feet long that requires 2 men to turn. With the hooks in place, the short end of the arm is complete. The engineer turns his attention to the long end, where the sling will attach. The sling is a pouch of heavy canvas or leather, sized to hold a stone ball 3 feet in diameter. The pouch is attached to the arm by 2 ropes, each 1 inch thick and 20 feet long. One rope is tied to the end of the arm with a permanent knot. The other rope ends in a loop that slips over a hook on the arm. When the arm swings upward and the sling reaches the top of its arc, the loop slips off the hook, releasing one end of the sling. The pouch opens, and the stone flies free. The timing of this release is critical. If the loop releases too early, the stone will fly too high and too short. If it releases too late, the stone will fly too low and too long. The exact point of release is determined by the position of the hook on the arm. By moving the hook forward or backward, the engineer can adjust the trajectory of the stone. But that is a problem for later, when the machine is complete and test firings can be conducted. For now, the engineer simply mounts the hooks at the calculated position, based on his experience and his understanding of the physics involved. The arm is now complete, 40 feet of oak, pivoting on an iron axle, with hooks for the counterweight at one end and hooks for the sling at the other. It is a lever of tremendous mechanical advantage. The counterweight, hanging 12 feet from the pivot, will fall perhaps 20 feet when the machine fires. The tip of the arm, 28 feet from the pivot on the other side, will travel through an arc of nearly 100 feet in the same time. This is the power of the machine. A slow, heavy fall translated into a fast, violent rise. But the machine is not yet complete. The counterweight remains to be built. The counterweight is a box, a simple wooden box, 12 feet long, 6 feet wide, and 6 feet deep. But it is no ordinary box. It is framed with oak timbers 1 foot square, braced and cross-braced to withstand the shock of sudden stops and starts. The sides are sheathed with oak planks 3 inches thick, edge-joined and doweled. The bottom is double-planked, 2 layers of 3-inch oak with the joints offset, so there are no continuous seams. The box is built on the ground beside the machine, assembled like a piece of furniture, the joints fitted with precision. When it is complete, it is a structure 6 feet on a side and 12 feet long, massive and solid. The interior volume is approximately 430 cubic feet. This box will be filled with weight. Lead would be ideal, lead being the densest commonly available material, but lead is expensive and in short supply. Stone is cheaper and more available. The engineer has had his laborers collect limestone rubble from a quarry 5 miles away, broken chunks of rock ranging in size from a man's fist to a man's head. This rubble has been stockpiled beside the foundation, a small mountain of grey stone. But stone alone will not be dense enough. The engineer calculates that limestone rubble, loosely packed, weighs approximately 100 pounds per cubic foot. 430 cubic feet would thus weigh about 43,000 pounds, or 21.5 tons. This is more than the engineer wants. The machine is designed for a counterweight of 10 tons. More weight would increase the power of the shot, but also increase the stress on the machine, potentially causing it to fail. The solution is to mix the stone with earth, packing it tightly to eliminate voids. Earth weighs about 90 pounds per cubic foot when compacted. By using a mixture of stone and earth, approximately half and half, the engineer can achieve an average density of about 95 pounds per cubic foot, giving a total weight of approximately 20 tons. But he does not want 20 tons. He wants 10 tons. Therefore, the box will not be filled completely. It will be filled halfway to a depth of 3 feet. But before the box can be filled, it must be hung from the arm. Iron straps, 2 inches wide and half an inch thick, are bolted to the top of the box at either end. These straps form loops that will slip over the hooks on the short end of the arm. The straps are forged by the blacksmiths, heated and bent to shape, the loops sized to fit the hooks with minimal clearance. Hanging the box is straightforward compared to mounting the arm. The box weighs, empty, perhaps 2 tons. The gin pole lifts it easily. It is positioned beneath the short end of the arm, which has been lowered by raising the long end with ropes. The box is lifted until its straps slip over the hooks. Then the ropes on the long end are released, and the arm settles, the weight of the box pulling the short end down. Now the box must be filled. This is labor for many hands. The laborers form a chain, passing baskets of stone and earth from the stockpile to the box. The first basket is poured in, the stones rattling and clanking as they fall. Then earth, shoveled in around the stones, filling the voids. More stones, more earth. The level in the box rises slowly. The engineer monitors the weight by measuring the deflection of the arm. As the box fills, the short end sinks lower, pulled down by the increasing weight. The engineer has marked a line on one of the uprights, a line that indicates where the arm should be when the counterweight reaches 10 tons. When the arm reaches this line, he calls a halt to the filling. But the weight is not quite right. The arm is a half-inch above the line, indicating that the counterweight is slightly too light. More earth is added, a few shovelfuls at a time, until the arm settles onto the mark. The engineer is satisfied. The counterweight is complete. The machine now stands in its full, terrible glory. The 2 A-frames rise 40 feet into the air, connected by the iron axle. The arm, 40 feet of tapered oak, pivots on the axle. The short end is pulled down by the weight of the counterweight box, now filled with 10 tons of stone and earth. The long end points at the sky, reaching upward like an accusing finger. The machine is nearly complete, but there are still details to attend to. The trigger mechanism must be installed. This is a simple system of ropes and pins that will hold the arm in the cocked position and release it when the engineer gives the command. The exact design is the engineer's own, developed over years of experience and refined with each machine he builds. The trigger consists of a heavy rope, one end tied to the end of the long arm, the other end running through a series of pulleys to a windlass. The windlass is a horizontal drum mounted on a stand, turned by men pushing on radial spokes. When the windlass is turned, it winds up the rope, pulling the long arm down against the weight of the counterweight. This is hard work. The men are pulling against 10 tons, using mechanical advantage to multiply their force. But even so, it requires 20 men pushing on the windlass to cock the machine. As the arm is pulled down, the short end rises, lifting the counterweight box 20 feet into the air. The potential energy of 10 tons raised 20 feet is enormous, waiting to be released. When the arm is fully cocked, the long end is pulled down until it is nearly horizontal. In this position, it is held by a trigger pin, an iron rod that passes through a hole in the arm and rests in a bracket. The trigger pin bears the full weight of the counterweight, preventing the arm from swinging upward. To fire the machine, the trigger pin is withdrawn. This is done by a separate rope, tied to the pin, running to a safe distance where the engineer can pull it while standing clear of the moving arm. When the pin is pulled, The arm is released. The counterweight falls. The arm swings upward. The sling whips through the air, and the stone is hurled toward the castle wall. But that is for tomorrow. Today, as the sun sets on the 10th day of construction, the engineer stands back and surveys his work. The machine is complete, a monument to human ingenuity and the application of physical principles. It is, in its way, beautiful. Not the beauty of a cathedral or a painting, but the beauty of pure function, every element shaped to its purpose, every joint calculated to bear its load. The engineer is tired. His hands ache from gripping tools, his back aches from bending over drawings, his mind aches from the constant vigilance required to keep 10,000 details in order. But he is satisfied. The machine will work. He knows this with the certainty that comes from experience, from understanding, from having built these machines before and seen them perform. Tomorrow they will fire the machine. They will load a stone into the sling, cock the arm, and release the trigger. The engineer will watch the stone arc through the air, will note where it lands, will calculate the adjustments needed to shift the impact point. It will take days, perhaps weeks, of testing and adjustment before the machine is firing consistently at the base of the south wall. But when that day comes, when the stones begin to strike their target with monotonous regularity, the castle's fate will be sealed. Stone walls, no matter how thick, cannot withstand repeated impacts from 300-pound projectiles. The mortar will crack, the stones will shift, and eventually the wall will collapse. And when the wall falls, the siege will be over. The castle will be taken, the garrison will surrender or be put to the sword, and the engineer will move on to the next siege, the next castle, the next machine. But tonight, he allows himself a moment of rest. He returns to his tent, where a simple meal of bread and cheese and wine waits. He eats slowly, methodically, tasting nothing, his mind still on the machine. After the meal, he spreads out his drawings one more time, checking his calculations, looking for errors, finding none. Finally, he allows himself to sleep, lying on a cot of rope and canvas, wrapped in a woolen blanket against the cold. Outside, the siege camp settles into its nightly routine. Fires burn low, guards pace their rounds, the sounds of 10,000 men gradually fade to snoring and the occasional challenge of a sentry. And beyond it all, on its hill, the castle waits, its walls pale in the moonlight, unaware that tomorrow its doom will be tested. The machine stands silent in the darkness, a skeleton of wood and iron waiting to be awakened, waiting to fulfill the purpose for which it was built, waiting to turn the slow fall of weight into the fast flight of stone, waiting to prove that human ingenuity can overcome any obstacle, can breach any wall, can bring down any fortress. Tomorrow it will speak, and the castle will listen. The morning arrives with a pale light that seems hesitant to touch the siege camp. The sky is the color of old iron, and a mist hangs low over the ground, clinging to the mud, softening the edges of tents and siege engines. The engineer wakes before dawn, as he always does. His body, trained by decades of early, starts to rouse itself when the darkness is just beginning to thin. He lies for a moment on his cot, feeling the ache in his joints, the stiffness in his back. He's not a young man anymore. This work takes its toll. But there is no time for complaint. The machine is built, yes, but it is not yet refined. The arm that now stands against the sky, that massive beam of oak weighing 2 tons, is the heart of the machine, and it requires attention. It requires understanding. It requires the kind of careful observation that separates a functioning siege engine from a pile of shattered timber. He rises, pulls on his boots, wraps a cloak around his shoulders against the morning cold, and steps out into the camp. The ground crunches beneath his feet, frost on the surface of the mud. His breath steams. Around him, the camp is beginning to wake. Fires are being rekindled. Men are emerging from tents, coughing, spitting, beginning the routines of another day. But the engineer's attention is on the machine. It dominates the landscape, even in the dim light. The two A-frames rise like the ribs of some great beast, and between them the arm extends, a 40-foot spine of oak. The short end is pulled down by the weight of the counterweight barks, now holding its 10 tons of stone and compacted earth. The long end points upward at perhaps 60 degrees from horizontal, reaching toward the lightning sky. The whole structure seems poised, balanced on a knife edge between stillness and violence. The engineer walks around the machine slowly, his eyes moving over every joint, every brace, every surface. He is looking for cracks, for shifts in the timber, for any sign that the forces contained within the structure are beginning to exceed the strength of the materials. He finds none. The oak is sound. The iron is secure. The machine has settled into itself overnight, the joints compressed under load, the timbers finding their natural positions. But now he must examine the arm more closely. The arm is not simply a beam. It is a carefully shaped lever designed to translate the slow fall of massive weight into the rapid rise of lesser weight. Every dimension of the arm has been calculated to optimize this translation. The thickness at the pivot point, where it mounts on the iron axle, is 2 feet square. This thickness is necessary to resist the bending forces that will try to snap the arm when it swings. At this point, when the machine fires, the arm will be subjected to forces exceeding 50 tons of compression on the upper surface and 50 tons of tension on the lower surface. Wood is strong in compression. The fibers can be squeezed together and they will resist, will hold. But wood is weak in tension. Pull on it hard enough and the fibers will separate, will tear apart, and the beam will snap. This is why the arm is thickest at the pivot. The thickness allows the neutral axis, the line through the center of the beam where there is neither compression nor tension, to remain well within the material. The top fibers compress, the bottom fibers stretch, but neither exceeds the breaking point. From the pivot point, the arm tapers. At 20 feet from the pivot, toward the long end, the cross-section has reduced to 18 inches square. At 30 feet, it is 14 inches square. At the very tip, where the sling will attach, it is 1 foot square. This taper serves two purposes. First, it saves weight. Every pound removed from the long end of the arm means 1 less pound that must be accelerated when the machine fires. Less weight means higher speed, means greater range. Second, the taper allows the arm to flex slightly when it swings. This flex stores energy like a spring, energy that is released at the moment the sling lets go, adding to the velocity of the stone. But flex is dangerous. Too much flex, and the arm will whip like a sapling in a storm, become uncontrollable, or worse, snap. The engineer has calculated the taper to allow just enough flex to be beneficial without crossing into the realm of failure. But calculation and reality do not always agree. The arm must be tested. He climbs onto the foundation, stepping carefully over the sleeper beams. He reaches up and grabs the long arm as high as he can reach, about 8 feet from the ground. He pulls down, putting his weight on it, feeling the resistance. The arm bends slightly, perhaps an inch over the 8-foot span. He releases it and it springs back. Good. There is flexibility there, but it is controlled, predictable. But flexibility also means vulnerability. When the arm swings and stops suddenly at the top of its arc, when the sling releases the stone and the arm whips back, the stresses in the wood will be enormous. The wood may split along the grain. The engineer has seen this happen on earlier machines, seen arms shatter into long splinters when the forces exceeded the wood's capacity to absorb them. To prevent this, the arm must be reinforced. The reinforcement comes in the form of iron bands, hoops of wrought iron that encircle the arm at critical points. The blacksmiths have been working on these bands for days, heating bars of iron to yellow heat, bending them around forms, welding the ends together to create complete circles. The first band goes at the pivot point, where the arm mounts on the axle. This band is 2 inches wide and half an inch thick, sized to fit snugly around the 2-foot square section of the arm. Getting the band onto the arm requires heat. The band has been forged slightly smaller than the arm, so small that it cannot be slipped over the wood at room temperature. The blacksmiths heat the band in their forge until it glows dull red. At this temperature, the iron expands, the diameter of the circle increasing by perhaps half an inch. The hot band is carried from the forge on long tongs, 4 blacksmiths working together, moving quickly before the iron cools. They position the band over the end of the arm and slide it along the beam to the pivot point. As the iron cools, it contracts, shrinking back to its original size, gripping the wood with tremendous force. The contraction squeezes the oak, compressing the fibers, creating a hoop stress that reinforces the beam against splitting. As the band cools, it makes small ticking sounds, the sound of iron contracting, of internal stresses settling. Steam rises from the wood where the hot iron touches it, a hiss of moisture being driven out. The smell of scorched oak fills the air, a sharp, acrid scent that catches in the throat. When the first band is fully cooled and seated, the process is repeated for the second band. This one goes 10 feet along the arm toward the long end, at a point where the cross-section is 18 inches square. The band is proportionally smaller, but the process is the same. Heat, carry, position, cool. The third band goes at 20 feet, the fourth at 30 feet. Each band adds weight, perhaps 50 pounds each, but the weight is worth it for the reinforcement they provide. With the bands in place, the engineer turns his attention to the surface of the arm. The wood has been planed smooth during construction, but now it must be treated to resist moisture. Wet wood is heavier than dry wood, and weight on the arm is the enemy of performance. More critically, wet wood swells, and if the wood swells within the iron bands, the bands will constrict it, crushing the fibers, weakening the beam. The treatment is a mixture of linseed oil and pine tar, heated together until they blend into a thick, viscous liquid. This mixture is applied to the arm with brushes made of hog bristles, worked into the grain of the wood. The oil penetrates, displacing moisture, sealing the surface. The tar remains on the surface, forming a protective coating that sheds water. The application takes hours. 2 men work with brushes, coating every inch of the 40-foot beam. The mixture is sticky, and it clings to everything it touches: the brushes, the men's hands, their clothes. The smell is overwhelming, a combination of the nutty scent of linseed oil and the sharp, resinous smell of pine tar. It is a smell that will linger on the arm for months, a smell that the engineer associates with machinery, with construction, with work. While the arm is being treated, the engineer focuses on the sling. The sling is, in many ways, the most ingenious part of the machine. It is a simple device, a pouch of leather or heavy canvas, attached to the end of the arm by 2 ropes. But this simple device doubles the effective length of the arm and therefore doubles the velocity of the stone. The principle is this: when the arm swings upward, the sling does not immediately follow. Instead, it drags along the ground, the stone in its pouch sliding across the earth. Only when the arm approaches the top of its arc does the sling lift off the ground and begin to swing. At this point, the sling is trailing behind the arm, connected to it by the 2 ropes. As the arm continues to rise, the sling swings upward, accelerating rapidly. At the perfect moment, one of the ropes releases, the pouch opens, and the stone flies free. The genius of the sling is that the stone travels through a much longer arc than the arm itself. The arm swings through an arc of perhaps 30 feet, from its lowest point to its highest. But the stone, trailing behind in the sling, swings through an arc of perhaps 60 feet. Twice the distance in the same time means twice the velocity, and velocity is everything. The kinetic energy of the stone is proportional to the square of its velocity. Double the velocity, and you quadruple the energy. But the sling only works if it releases at exactly the right moment. Too early, and the stone will be thrown too high, arcing up into the sky and falling short of the target. Too late, and the stone will be thrown too low, driven into the ground short of the target. The timing of the release is controlled by a simple but critical mechanism: the release pin. One of the two ropes that attach the sling to the arm is tied permanently. This rope is 3/4 inch hemp, tarred to resist rot, knotted to a bronze ring at one corner of the sling pouch. The rope runs up to the end of the arm and is tied off to an iron ring bolted through the wood. This rope will never release. It is the anchor. The second rope is also 3/4 inch hemp, also tarred, but instead of being tied off, it ends in a loop. This loop slips over a release pin, an iron hook mounted on the arm. When the arm swings upward, the loop slides along the pin, held in place by the weight of the stone. But at the top of the arc, when the arm stops and jerks backward, the loop slides off the end of the pin. The pouch opens, and the stone is released. The position of the release pin determines the timing of the release. If the pin is mounted far out on the arm, near the tip, the loop will be held longer, and the stone will release later in the arc. If the pin is mounted closer to the pivot, the loop will slip off earlier. By moving the pin forward or backward along the arm, the engineer can adjust the trajectory of the stone with precision. But the pin position is not the only variable. The length of the sling ropes also affects the trajectory. Longer ropes mean the sling trails farther behind the arm, increasing the arc length and therefore the velocity. But longer ropes also mean the sling is more likely to tangle or to strike the ground on the backswing after release. The engineer has calculated that ropes of 20 feet are optimal for this machine, long enough to provide good velocity, but short enough to be manageable. The sling pouch itself is a critical component. It must be strong enough to hold a 300-pound stone without tearing, yet flexible enough to collapse and release cleanly when the rope lets go. The engineer has specified a pouch made of bull hide, the thick leather from the back and shoulders of a large ox. The leather is cut into a rectangle 2 feet wide and 3 feet long, folded and stitched along the edges to create a cup-shaped pouch. The stitching is done with waxed linen thread, the kind used for saddle making, strong and rot-resistant. The seamstress works with a curved needle, forcing it through the thick leather with a leather palm, a pad of hard leather worn on her hand to protect it as she pushes the needle through. Each stitch is pulled tight, the thread biting into the leather, creating a seam that will hold under stress. At each corner of the pouch, a bronze ring is sewn in, the ring captured in a loop of leather that is folded over and stitched. These rings provide the attachment points for the ropes. Bronze is used instead of iron because it does not rust, and rust could weaken the attachment at a critical moment. The completed sling is a beautiful piece of work, the leather smooth and supple, the stitching even and tight, the bronze rings glinting in the light. It weighs perhaps 10 pounds, negligible compared to the stone it will carry, but it represents hours of skilled labor. Now the sling must be attached to the arm. The engineer climbs a ladder leaned against the long end of the arm, now pointing upward at 60 degrees. At the tip of the arm, 28 feet from the pivot, 2 iron rings are bolted through the wood. These rings are 6 inches in diameter, forged from iron bars bent into circles and welded. They project from the sides of the arm, one on the left, one on the right. The first rope, the permanent anchor rope, is tied to the left ring. The knot is a bowline, a loop knot that will not slip under load. The engineer ties it himself, forming the loop, passing the working end through, around, and back. He pulls it tight, testing it with his full weight. The knot holds. He ties a second bowline a foot below the first, a backup in case the first knot fails. Then he seals both knots with a wrapping of tarred twine, binding the working end to the standing part, ensuring that the knots cannot work loose. The second rope, the release rope, ends in a spliced loop. The splice is a back splice, the strands of the rope unlaid, woven back into themselves to form a permanent loop. The loop is sized to fit loosely over the release pin. The engineer tests the fit, slipping the loop over the pin, pulling on it, feeling how much force is required to make it slide. Not much. The loop moves easily along the pin. Too easily, perhaps. If the loop slips off prematurely during the cocking process, The sling will release with no stone in it, and the ropes will whip around with potentially deadly force. To prevent premature release, the engineer adds a safety pin, a wooden peg that can be inserted through a hole in the release pin, blocking the loop from sliding off. The safety pin will be removed just before firing, ensuring that the loop can only release when intended. With the sling attached, the engineer climbs down from the ladder and examines the arrangement. The two ropes hang down from the tip of the arm, the sling pouch dangling between them, empty for now. The engineer pulls on the ropes, testing their attachment, checking for weak points. Everything is secure. But there is another element to the sling system that must be prepared: the runway. When the machine fires, the stone will not immediately lift off the ground. For the first part of the arm's swing, the stone will drag along the earth, sliding in its pouch, accelerating from 0 to perhaps 20 miles per hour before it finally lifts off. If the ground is rough, if there are obstacles, the stone will catch, the sling will snag, and the shot will fail. The runway is a prepared surface, a strip of ground directly in line with the machine's aim, extending about 30 feet forward from the machine. This surface must be smooth, level, and hard. The engineer has had his laborers excavate the topsoil, removing the mud and exposing the clay beneath. The clay has been wetted and tamped, beaten with wooden mallets until it is as hard as concrete. Then it has been covered with a layer of sand, smoothed with wooden floats until it is perfectly level. The result is a surface like a road, hard and smooth. The engineer walks along it, feeling with his feet for irregularities. He finds a small rise, perhaps half an inch high, and has it scraped down. He finds a depression, a tiny hollow, and has it filled with more sand and tamped. When he is satisfied, he paces off the distance, ensuring that the runway extends far enough. 30 feet should be sufficient. Beyond that, the stone will have lifted off, will be airborne, and the condition of the ground will not matter. With the arm reinforced, the sling attached, and the runway prepared, the engineer turns his attention to the cocking mechanism. The machine in its current state rests with the long arm up and the short arm down, the counterweight hanging at ground level. To fire the machine, the long arm must be pulled down, raising the counterweight high into the air. This requires an enormous amount of work, in the physics sense, force applied over distance. 10 tons of counterweight must be lifted 20 feet, which is 200,000 foot-pounds of work. Human muscles can provide this work, but not easily. A strong man can perhaps exert a continuous pull of 100 pounds. To lift 10 tons, or 20,000 pounds, would require 200 men pulling continuously. The siege camp does not have 200 men to spare for cocking a single machine. The solution is mechanical advantage. By using a system of pulleys and winches, the force required from each man can be reduced at the cost of the distance they must pull. Instead of pulling the full weight directly, the men pull a fraction of the weight over a proportionally longer distance. The cocking system for this machine uses a combination of pulleys and a large windlass, sometimes called a squirrel cage. The squirrel cage is a horizontal drum, 6 feet in diameter and 10 feet long, mounted on an axle supported by heavy timber frames. Around the circumference of the drum are 16 wooden spokes, each projecting 2 feet beyond the surface of the drum. Men walk inside this drum, stepping on the spokes like the rungs of a ladder, their weight causing the drum to rotate. As the drum rotates, a rope winds around its circumference. This rope is thick, 2 inches in diameter, made of the best hemp. It must be strong enough to sustain a load of several tons without breaking. The rope runs from the drum, through a series of pulleys mounted on a timber framework, to the end of the long arm of the trebuchet. The pulley system provides mechanical advantage. A simple single pulley provides no mechanical advantage, merely changes the direction of the rope. But a compound pulley system, where multiple pulleys are rigged in series, can multiply the force significantly. The engineer has designed a system with 6 moving pulleys, providing a mechanical advantage of 12 to 1. This means that, for every pound of force applied at the windlass, 12 pounds of force are applied to the arm. But mechanical advantage comes at a price. To lift the counterweight 20 feet, the rope at the windlass must be pulled 240 feet, 12 times the distance. The men walking inside the drum must walk 240 feet to cock the machine once. The drum has been built on the ground beside the machine, a massive structure of oak timbers and iron fittings. The axle is an oak trunk 1 foot in diameter, supported by bearings carved into heavy timber uprights. The bearings are lined with bronze bushings, greased with animal fat. The drum itself is constructed of staves, like a barrel, each stave 3 inches thick and 10 feet long, edge-jointed and bound with iron hoops. The spokes are oak dowels 3 inches in diameter, inserted into holes drilled through the staves. Each spoke projects inward into the center of the drum, where it will serve as a foothold for the men, and outward beyond the surface, where it acts as a reinforcing element, preventing the staves from spreading under load. When the drum is complete, it is mounted on its axle and tested. 4 men climb inside and begin walking. The drum rotates smoothly, the axle turning in its greased bearings with a low rumble. The engineer watches, listening for any grinding or binding. The rotation is smooth. He is satisfied. The rope is attached to the drum by passing it through a hole in the staves and knotting it around one of the internal spokes. The rope then wraps around the drum 3 times before running out to the pulley system. The 3 wraps ensure that even under load, the rope will not slip on the drum. The pulley system is mounted on a wooden frame positioned between the machine and the drum. The frame is built of heavy oak timbers, braced against lateral forces. 6 pulleys are mounted on this frame, each pulley a bronze wheel 8 inches in diameter, grooved to accept the rope. The pulleys are arranged in 2 groups of 3, one group fixed to the frame, the other group attached to a movable block connected to the arm. The rope is threaded through the pulleys in a specific pattern, creating the mechanical advantage. It starts at the drum, runs to the first fixed pulley, down to the first moving pulley, up to the second fixed pulley, down to the second moving pulley, and so on. The final run of rope attaches to the end of the long arm. Setting up this system takes most of a day. The rope must be threaded carefully, ensuring that it runs smoothly through each pulley, that it does not cross itself, that it maintains the correct tension. When it is complete, the engineer tests it. Men enter the drum and begin walking. The drum rotates. The rope tightens. The pulleys turn with a low creaking sound, and slowly, inch by inch, the long arm begins to descend. The arm moves perhaps 6 inches before the engineer calls a halt. He examines the pulley system, checking for any signs of problems. One pulley is rubbing against its mounting, the friction causing it to turn reluctantly. He has the mounting adjusted, shifting the pulley outward by a 1/4 inch. The test resumes. The arm continues to descend, smoothly now, all the pulleys turning freely. When the arm has descended 3 feet, the engineer calls another halt. He is testing the system incrementally, ensuring that it can handle the load before committing to a full cocking. So far, everything is working as designed. The mechanical advantage is correct. The men in the drum are walking easily, not straining, yet the arm is moving against the weight of the counterweight. But there is another component to the cocking system that has not yet been tested: the ratchet. The ratchet is a safety mechanism, a device that prevents the arm from swinging back up if the men in the drum stop walking or if the rope breaks. Without a ratchet, the stored energy in the raised counterweight would be released instantly. If anything went wrong, the arm would whip upward with lethal force, and anyone near the machine could be killed. The ratchet consists of a toothed wheel mounted on the axle of the drum and a pawl, a lever that engages the teeth. The wheel is iron, 2 feet in diameter, with 30 teeth cut into its circumference. Each tooth is shaped like a right triangle with one vertical face and one sloped face. The pawl is an iron bar, hinged at one end, weighted at the other, with a hardened steel tip that engages the teeth. When the drum rotates in the cocking direction, the pawl rides up the sloped faces of the teeth with a clicking sound. Click, click, click. Each click represents 1/30th of a rotation, or about 7 inches of rope wound onto the drum. If the drum tries to rotate backward, the pawl drops into the vertical face of a tooth, locking the wheel and preventing any motion. The engineer tests the ratchet by having the men in the drum walk forward 3 steps, then stop. The drum continues to rotate for perhaps a quarter turn, coasting on its momentum, then the pole catches with a sharp clack. The drum stops instantly. The rope thrums with tension but does not break. The arm remains in position, held by the ratchet. The men in the drum step backward, trying to reverse the rotation. The drum does not move. The ratchet is holding. The engineer is satisfied. Now he orders a full cocking. The men in the drum, 8 of them now, begin walking at a steady pace. The drum rotates. The rope winds onto its surface, layer upon layer, the diameter of the coil increasing as more rope is wound on. The pulleys turn, the rope running through them with a soft hissing sound. The long arm descends, degree by degree. As the arm descends, the short arm rises, lifting the counterweight box off the ground. The box is heavy, 10 tons of rock and earth, and it resists being lifted. But the mechanical advantage is sufficient. The men walk, the drum turns, the arm descends, the box rises. The engineer watches the counterweight box carefully. As it rises, it swings slightly, pendulum-like, the motion damped by the mass. He watches for any signs of structural failure, any cracks in the planking, any bending of the frame. The box is solid. It rises smoothly. The ratchet clicks steadily. Click, click, click. The sound is rhythmic, almost hypnotic. It marks the progress of the cocking, each click bringing the machine closer to its fully armed state. The men in the drum settle into the rhythm, their footfalls synchronized with the clicks. After 10 minutes of walking, the arm is approaching horizontal. The counterweight box is now 15 feet off the ground, swaying gently at the end of its chain. The engineer watches the angle of the arm, comparing it to a marked post he has set up as a reference. When the arm reaches the correct angle, he will call a halt. But the arm does not stop at horizontal. The men continue walking, and the arm descends past horizontal, the long end now lower than the pivot point. This seems counterintuitive. Why lower the arm past horizontal? But there is a reason. When the arm is past horizontal, when the long end is actually lower than the short end, the counterweight is at its highest point and the stored energy is at its maximum. More importantly, when the arm is past horizontal, it is more stable in the cocked position. The weight of the counterweight is pulling downward and backward, pressing the arm against the trigger mechanism, rather than trying to lift it. The arm descends to 15 degrees past horizontal before the engineer calls a halt. The men in the drum stop walking. The ratchet catches with a final click. The arm is cocked. The counterweight box hangs 20 feet in the air, motionless, heavy with potential. The engineer examines the trigger mechanism. This is a simple but critical system, the device that holds the arm in the cocked position and releases it on command. The trigger consists of a hook, a heavy iron hook bolted to the foundation, positioned so that it catches the underside of the long arm when the arm is pulled down past horizontal. The hook has a curved upper surface, shaped so that the arm can slide over it as it descends, but cannot slide back when it tries to rise. The arm rests on this hook now, the weight of the counterweight pressing the wood against the iron. The engineer inspects the contact point. The iron has bitten slightly into the oak, compressing the fibers, but the wood is holding. He tests the security of the arrangement by pushing on the arm, trying to lift it. It does not budge. The hook is holding firm. But the trigger must also be capable of releasing the arm. This is accomplished by a release mechanism, a lever that pivots the hook out of the way, allowing the arm to swing free. The lever is a wooden pole 10 feet long, hinged at one end and weighted at the other. The pole runs from the hook to a position 20 feet away, well clear of the machine's swing radius. To fire the machine, the engineer or an assistant will pull on a rope attached to the weighted end of the lever. This will pivot the hook downward, disengaging it from the arm. The arm will be free to swing, the counterweight will fall, and the machine will fire. But before firing, the stone must be loaded. The stone is a sphere of limestone, carved by stonemasons over the course of a week. It started as a rough block of stone weighing perhaps 500 pounds, cut from the same quarry that supplied the rubble for the counterweight. The stonemasons worked the block with hammers and chisels, knocking off the corners, rounding the edges, gradually shaping it into a sphere. The shaping is critical. A sphere is the most aerodynamic shape, offering the least air resistance as it flies. It is also the shape that packs the most mass into the smallest volume, making it easier to fit into the sling pouch. And it is the shape that rolls most easily along the runway, reducing friction during the initial acceleration. The finished stone is 3 feet in diameter and weighs 300 pounds. Its surface is relatively smooth, the chisel marks worn away by final smoothing with abrasive stone. It sits now beside the machine, resting on a wooden cradle, waiting. Loading the stone is a multi-person operation. The stone must be lifted and carried to the sling, positioned in the pouch, and secured so that it will not roll out prematurely. 6 men are assigned to this task. They bring a sling of hemp rope, looped under the stone and knotted at the top to form a handle. Each man grips the rope, 3 on each side. On a counted signal, they lift together. The stone rises slowly off its cradle. 300 pounds divided among 6 men is 50 pounds each, a manageable load. But the stone is awkward, round and heavy, trying to slip out of the rope sling. The men adjust their grips, leaning back to balance the weight. They begin to walk, shuffling in unison, carrying the stone toward the machine. The sling pouch lies on the ground at the front of the machine, in line with the runway. The men lower the stone carefully, settling it into the leather pouch. The pouch deforms under the weight, the leather stretching, conforming to the curve of the stone. The stone settles into place with a solid thump. The engineer checks the positioning. The stone must be centered in the pouch, with the 2 rope attachments balanced on either side. If the stone is off-center, it will twist in the sling during the swing, potentially causing it to release at an unpredictable angle. He adjusts the stone slightly, rolling it within the pouch until it is perfectly centered. Now the sling ropes must be checked one final time. The engineer climbs his ladder and inspects the attachment points. The anchor rope is secure, the knot tight. The release rope is positioned correctly on its pin, the loop lying flat against the iron. He checks the safety pin, the wooden peg that prevents premature release. It is in place, inserted through the hole in the release pin, blocking the loop. He climbs down and walks around the machine, his eyes moving over every component. The A-frames are solid, the bracing is tight, the axle is greased, the arm is reinforced, the sling is ready, the stone is loaded. Everything is prepared. But he is not ready to fire. Not yet. First, the machine must be aimed. Aiming a trebuchet is a matter of geometry and trial. The machine throws the stone in a parabolic arc, the shape of the arc determined by the velocity and angle of release. The velocity is determined by the counterweight, the arm length, and the sling length, all of which are fixed. The angle of release is determined by the position of the release pin, which can be adjusted. But even with the release pin in the calculated position, the first shot will almost certainly miss. There are too many variables, too many unknowns. The friction on the runway, the flexibility of the arm, the stretch in the ropes, the weight distribution in the stone. All of these factors affect the trajectory in ways that cannot be fully predicted. The machine must be test-fired, the impact point observed, and adjustments made. But test firing will have to wait for tomorrow. The light is fading now, the sun dropping toward the horizon, painting the sky in shades of copper and ash. The siege camp is settling into its evening routine. Cooking fires are being lit, meals are being prepared. The smell of wood smoke and boiling porridge drifts across the muddy ground. The engineer allows himself a moment of satisfaction. The machine is built. It is cocked. It is loaded. It is ready. Tomorrow it will speak. Tomorrow it will hurl its first stone toward the castle wall. Tomorrow the siege will enter a new phase. But tonight there is peace. The machine stands silent, the arm locked in its cocked position, the counterweight hanging in the air, the stone resting in its sling. Potential energy waiting to be released. Physics frozen in a moment of stillness. The engineer walks around the machine one more time as the darkness gathers. He runs his hand along the sleeper beams, feeling the solidity of the foundation. He touches the uprights of the A-frames, feeling the grain of the wood, the slight roughness where the bark has been hewn away. He looks up at the arm, a dark line against the darkening sky, pointing upward at an angle, held by the trigger. The machine is beautiful in its way, not the beauty of art, but the beauty of function. Every element serves a purpose. Every joint is calculated. Every dimension is deliberate. It is a pure expression of physical law, of leverage and gravity and momentum. And tomorrow it will prove those laws, will demonstrate with violent clarity that stone walls, for all their seeming permanence, are no match for human ingenuity. But that is for tomorrow. Tonight the machine rests. The potential waits. The castle on its hill sleeps unaware. The engineer returns to his tent. Inside, a single candle burns, casting flickering shadows on the canvas walls. He has a simple meal, bread and cheese, and a cup of watered wine. He eats without tasting, his mind still on the machine, running through the calculations one more time, checking his mental model against the physical reality he has built. After the meal, he spreads out his drawings. The parchment is worn now, creased from being rolled and unrolled, stained with mud and grease and the marks of countless corrections. But the drawings are accurate. He has built what he designed. Tomorrow will tell if he designed it correctly. He allows himself a small luxury, a moment of reflection. This is his fifth siege engine, his fifth trebuchet. Each one has been larger than the last, more powerful, more refined. Each one has represented the accumulated knowledge of a lifetime devoted to understanding how forces work, how materials behave, how to bend wood and iron to his will. He thinks back to his first machine, built 30 years ago when he was a young man, barely more than an apprentice. That machine was small, crude, more likely to shake itself apart than to damage a castle wall. He had learned by trial and error, by watching machines fail, by understanding why they failed. Each failure had taught him something. Each success had built his confidence. This machine, this fifth machine, is the culmination of those 30 years. It incorporates everything he has learned. The proportions are optimized. The materials are the best available. The construction is meticulous. If this machine fails, it will not be due to any flaw in his understanding or his execution. It will be simply the nature of war, the unpredictability of combat, the thousand small chances that can turn success into failure. But he does not believe it will fail. He has built it too well. He has checked it too carefully. He knows, in the deep intuitive way that comes from experience, that it will work. He rolls up the drawings and sets them aside. He blows out the candle. In the darkness, he can hear the sounds of the camp. Voices, laughter, the clang of a hammer on metal from a smithy that is working late, the distant challenge of a sentry. And beyond it all, the silence of the castle, sitting on its hill, waiting. The engineer lies down on his cot. The ropes creak under his weight. He pulls the woolen blanket over himself. The night is cold, and he can see his breath even in the darkness of the tent. But he is warm enough. He is always warm enough. Years of sleeping in siege camps have inured him to discomfort. He closes his eyes, but sleep does not come immediately. His mind is still working, still calculating, still planning. Tomorrow they will fire the machine for the first time. He will observe the flight of the stone, will see where it lands, will calculate the necessary adjustments. It will take days, perhaps weeks, of test shots and corrections before the machine is reliably hitting the target. Each shot will consume time and resources. Each shot will warn the defenders of what is coming. But once the machine is zeroed in, once it is consistently striking the base of the south wall, the siege will effectively be over. It is only a matter of time before the wall falls. Stone cannot withstand repeated impacts from 300-pound projectiles. The mortar will crack, the stones will shift, and eventually a section of wall will collapse inward, creating a breach through which the besieging army can assault. The defenders know this. They have seen siege engines before. They will attempt to counter the machine, perhaps by making sorties from the castle to burn it, or by building protective mantlets within the castle to shield against the flying stones. But the engineer has planned for these contingencies. The machine is positioned far enough from the castle that sorties will be difficult, and no mantlet, no matter how sturdily built, can protect against the kind of kinetic energy this machine will deliver. The engineer's mind begins to slow, the thoughts becoming less focused, more dreamlike. He sees the machine in his mind's eye, sees it firing in slow motion. The trigger releasing, the arm swinging upward, the sling trailing behind, the stone accelerating, the moment of release, the arc through the air, the impact. He sees the wall crumbling, sees stone flying, sees dust rising. And then, finally, he sleeps. The camp settles into quiet. The fires burn down to coals. The voices fade. The guards pace their rounds, their footsteps squelching in the mud. The stars wheel overhead, cold and distant. The castle on the hill is dark, its windows unlit, its walls solid and seemingly eternal. And between the camp and the castle, the machine stands, silent, waiting. The arm points upward at its 15-degree angle, locked against the night sky. The counterweight box hangs 20 feet in the air, motionless, its 10 tons of stone and earth held in place by nothing but wood and iron and the laws of physics. The long arm presses down against the trigger hook, the weight of the counterweight trying to pull it upward, the hook resisting, holding firm. Inside the sling pouch, the stone rests on the prepared runway, 300 pounds of carved limestone, centered and balanced. The two ropes extend upward to the tip of the arm, taut, ready. The release rope loops over its pin, held in place by the wooden safety peg. Everything is poised, balanced on the edge between stillness and motion. The potential energy stored in the machine is enormous. 10 tons raised 20 feet represents 200,000 foot-pounds of energy, enough to accelerate the 300-pound stone to a speed exceeding 100 miles per hour. That energy waits, patient, contained, ready to be released at a touch. The machine is a monument to human understanding of the physical world. It is built on principles discovered by ancient Greek mathematicians, refined by Roman engineers, perfected by medieval craftsmen. It represents the accumulated knowledge of centuries, distilled into 40 feet of oak and iron. The lever, the fulcrum, the mechanical advantage of the counterweight, the multiplication of velocity through the sling. These are not magic. They are physics, the fundamental laws that govern how matter and energy interact. The engineer understands these laws, not in the abstract way of a scholar, but in the concrete way of a builder. He knows that if he doubles the length of the sling ropes, he will increase the velocity of the stone. He knows that if he adds weight to the counterweight, he will increase the range. He knows these things not because he has read them in books, but because he has built machines and observed their behavior. And now he has built his greatest machine. It stands in the darkness, waiting for tomorrow, waiting to prove itself, waiting to transform potential into kinetic, stillness into violence, silence into thunder. The guards walk past it on their rounds, barely glancing at it. To them, it is just another piece of siege equipment, another tool of war. They do not understand the forces it contains, the violence it is capable of unleashing. They see only wood and rope and iron, familiar materials arranged in an unfamiliar way. But the engineer understands, and tomorrow everyone will understand. The night deepens, the temperature drops. Frost forms on the timbers of the machine, a delicate crystalline coating that makes the wood shimmer in the starlight. The frost coats the arm, the frame, the counterweight box. It coats the stone in its sling, turning the grey limestone white. The silence is profound. Even the usual sounds of the siege camp have faded. The men are asleep, exhausted by the day's labor. The animals are quiet, the horses and oxen and mules standing in their pickets, heads low, dozing. The world seems to have paused, holding its breath, waiting for dawn. The castle on its hill is equally silent. Behind those thick stone walls, the garrison sleeps, unaware of the doom being prepared for them. The sentries on the walls pace back and forth, looking down at the siege camp below, seeing the scattered fires, the dark shapes of tents, the bulk of the siege engine standing between the camp and the castle. They have seen siege engines before. They are not overly concerned. Stone walls have defended against attackers for centuries. They will defend again. But they do not know what this particular machine is capable of. They do not know that the engineer has calculated every dimension, tested every material, refined every mechanism. They do not know that tomorrow, when the first stone arcs through the sky and crashes into their wall, it will be only the first of hundreds. They do not know that the wall they trust, the wall they believe is impregnable, is already doomed. The machine knows. It waits in the darkness, patient and implacable. It is a tool without consciousness, without intent. But it has been built for a purpose, and it will fulfill that purpose. When the trigger is released, it will not hesitate. It will not fail. It will simply obey the laws of physics, transforming potential energy into kinetic energy, hurling stone against stone, battering and breaking until the wall falls. The engineer sleeps, dreaming of trajectories and impact points. His hands twitch slightly as he dreams, acting out the motions of pulling ropes, turning winches, making adjustments. His breathing is slow and steady. His face is calm. He is at peace, confident in his work. Outside, the machine stands vigil. The frost thickens on its timbers. The stars wheel overhead. The night passes slowly, measured in heartbeats and breaths, and the slow creeping of the constellations across the sky. And in the suspended arm, in the hanging counterweight, in the loaded sling, the potential waits. The physics are set. The forces are balanced. The trigger holds. Tomorrow, the balance will be broken. Tomorrow, the forces will be released. Tomorrow, the machine will wake and speak, and the castle will begin to crumble. But tonight, there is only silence. Only the cold stars and the frosted wood and the patient waiting. The potential hangs in the air like a held breath, like a drawn bow, like a wave poised to crash. The machine stands against the night sky, its arm raised, its weight balanced, its purpose clear. It is a promise of violence, a testament to human ingenuity, a physical embodiment of mathematical principles. It is 40 feet of oak and iron and rope, built by human hands according to human plans, ready to perform the work for which it was designed. And as the massive wooden arm stands locked against the night sky, holding the weight of the earth in balance, the camp sleeps. The physics are set. Sleep well.